reality appears solid. Measurements seem objective. When two observers look at the same event, they are expected to see the same thing, the same distance, the same duration, the same sequence of events. This expectation runs so deep that questioning it feels absurd. But physics does not confirm this intuition. Albert Einstein demonstrated that observers moving relative to one another will measure different values for time, distance, and simultaneity, and that both observers are correct. This is not error. It is not approximation. It is not a matter of interpretation. The measurements genuinely differ, and the difference is embedded in the structure of physical reality. Two observers can witness the same pair of events and legitimately disagree about whether those events happened at the same time. They can measure the same object and report different lengths. They can time the same process and record different durations. They are consequences of how space-time is organized. What remains invariant, what does not change, are the physical laws themselves. The laws governing light, motion, and causality hold universally, but the measured values extracted from those laws depend on the observer's state of motion. This is not philosophy, it is physics, and it changes what it means for something to be real. The assumption of objective reality is not arbitrary, it emerges from daily experience. Objects persist, measurements agree. Observers separated by distance can coordinate their descriptions of the world and find consistency. When two people measure the length of a table, they obtain the same result. When they time a falling object, their stopwatches agree. When they observe a sequence of events, one thing happening, then another, they concur on the order. This repeatability is the foundation of science. It is why measurement works. It is why physical theories can be tested. This consistency reinforces a natural conclusion that reality exists independently of observation. The table has a length whether or not anyone measures it. Events happen in a definite order, whether or not anyone witnesses them. Time passes at a universal rate, and space extends uniformly in all directions. Disagreement between observers is attributed to error, incomplete information, or distortion. If two measurements differ, one must be wrong, or both must be affected by some overlooked influence. The idea that both could be correct without error or interference seems incoherent. This intuition is so strong that it persisted through centuries of precise scientific inquiry. It survived the development of mechanics, optics, and electromagnetism. It was built into the mathematical structure of classical physics, and it was incorrect. Before Einstein, physics treated space and time as absolute. Space was an infinite, unchanging stage on which events occurred. Time was a universal parameter, flowing identically for all observers. If two events were simultaneous, they were simultaneous for everyone. If an object had a certain length, that length was intrinsic to the object. Observers might move through space, but the space itself remained fixed. Clocks might be positioned differently, but they all measured the same underlying time. The laws of physics were understood to operate within this fixed framework, and the framework itself was never questioned. Newton's mechanics, which governed motion and force, assumed absolute time. Maxwell's equations, which described light and electromagnetism, seemed to imply an absolute reference frame, a medium through which light propagated. The expectation was that careful experiments would reveal this frame, anchoring all motion to a universal standard. Those experiments failed. Light behaved in ways that contradicted the assumption of an absolute frame. Its speed did not vary with the motion of the source or the observer. This result was initially treated as anomalous, a puzzle to be resolved within the existing framework. Einstein recognized that the framework itself was the problem. The constancy of light speed was not an anomaly. It was a constraint, a fundamental property of nature that required space and time to be rethought. Absolute space and absolute time could not coexist with the observed behavior of light. Something had to give. What gave was the independence of space and time. They merged into a unified structure. space-time, where measurements of duration and distance became entangled with the observer's state of motion. Special relativity, published in 1905, dismantled the assumption of universal agreement. Einstein showed that observers moving at constant velocities relative to one another would measure time and space differently, and that these differences followed precise mathematical rules. Consider two observers, one stationary, the other moving at high speed. A light pulse is emitted from a source midway between two detectors. The stationary observer sees the pulse reach both detectors simultaneously. The moving observer does not. For the moving observer, one detector is approaching the light, the other receding. The light reaches them at different times. Both descriptions are valid. Simultaneity is not absolute. It depends on the observer's motion. The same principle applies to time intervals. A clock moving relative to an observer ticks more slowly than a stationary clock. This is not an illusion caused by signal delay. It is not mechanical wear on the clock. It is a difference in how time itself elapses for objects in motion. The moving clock genuinely experiences less time. Distance is likewise observer-dependent. An object moving at high speed is measured to be shorter along the direction of motion than it is when stationary. The object does not physically compress. The shortening is a consequence of how space and time are measured in different frames of reference. These are not distortions imposed on an underlying objective reality. They are features of space-time itself. The measurements are as real as any measurement can be, and they differ. This creates a tension that seems unresolvable. If reality is observer-dependent, does it become arbitrary? If measurements differ, what is actually true? Observer-dependence is not subjectivity. It is not a matter of opinion or perception. It is a structured relationship between measurements made in different reference frames. A reference frame is a coordinate system, a way of assigning positions and times to events. Different frames correspond to different states of motion. An observer at rest defines one frame. An observer at rest defines one frame. An observer moving at constant velocity defines another. Neither frame is privileged. Physics works identically in all inertial frames. What changes between frames are the coordinate values, the specific numbers assigned to time, distance, and simultaneity. What does not change are the physical laws. Maxwell's equations hold in every frame. The speed of light is constant in every frame. Causality is preserved in every frame. This invariance is what keeps reality from collapsing into chaos. The laws constrain how measurements can differ. They enforce consistency. They ensure that while observers disagree about coordinate-dependent quantities, they agree on coordinate-independent ones, on the outcomes of physical processes, on the structure of cause and effect, on the predictions of theory. Observer dependence means that measurements are frame relative, not that they are arbitrary. The relativity of simultaneity, time dilation, and length contraction are all derived consequences of the invariance of physical law. They follow necessarily once the constancy of light and the equivalence of inertial frames are accepted. But this raises a deeper question. How does space-time enforce this structure? What mechanism underlies the dependence of measurement on motion? The mechanism is space-time geometry. Space and time are not separate entities, but components of a four-dimensional continuum. Events are points in this continuum, and the separation between events is described by an interval, a quantity that mixes spatial and temporal components. Different observers decompose this interval differently. What one observer experiences as purely spatial separation, another may experience as a mix of space and time. The interval itself, the space-time separation, is invariant. All observers agree on it. But how that interval divides into space and time depends on the observer's motion. This division is frame-dependent. Time dilation and length contraction emerge directly from this geometry. When an observer measures the duration between two events that occur at the same location in a moving frame, they are measuring a longer interval than the observer moving with those events. The space-time path differs depending on the frame. Simultaneity is similarly geometric. Events that lie on a surface of constant time in one frame lie on a tilted surface in another. The tilt depends on relative velocity. There is no universal now. Each frame defines its own present moment, and these definitions differ. This is not a limitation of measurement. Space-time does not provide a single universal way to slice events into space and time. It provides infinitely many ways, each corresponding to a different state of motion, all equally valid. The observer dependence of reality is a consequence of this geometric structure. Measurements depend on the frame because frames correspond to different ways of navigating space-time. The physical laws remain invariant because they are written in terms of quantities that transcend any particular frame. Intervals, four vectors, tensors. This is not abstract theory. It has measurable consequences. Particle accelerators exploit time dilation to extend the lifetimes of unstable particles, allowing them to travel distances they could not otherwise reach. GPS satellites correct for relativistic effects, both from their motion and from their position in Earth's gravitational field, to maintain precision. Without accounting for observer dependence, the system would fail. High-energy astrophysics depends on relativistic calculations. The behavior of objects near light speed, the structure of black holes, the propagation of gravitational waves, all require treating space-time as observer-dependent. Classical assumptions produce incorrect predictions. Even the synchronization of clocks across distributed systems requires relativistic correction. Time does not flow uniformly. Coordination requires accounting for the relative motion of clocks and the finite speed of signals. Observer dependence is not a curiosity. It is embedded in the functioning of modern technology and the interpretation of experimental data. Reality is observer dependent. Time, space, and simultaneity are not absolute. Observers in relative motion measure different values for these quantities, and both sets of measurements are correct. This does not mean reality is arbitrary. It means reality has a deeper structure than classical physics assumes. That structure, space-time, enforces consistency through the invariance of physical laws. What changes is how those laws are expressed in coordinates. What remains fixed is their form and their prediction. Einstein's insight was to recognize that the constancy of light demanded this restructuring. The failure of observers to agree on simultaneity was not a problem to be solved. It was a feature to be understood. The observer dependence of measurement was not a breakdown of objectivity. It was a revelation of how objectivity operates in a relativistic universe. The laws are invariant. The measurements depend on the observer. Both statements are true and they do not conflict. That is the nature of physical reality.